Hello, everyone. Today's lecture is about standing waves, and we'll also cover the resonance in this lecture. So let's move on and refresh our memories with what we have dealt with before. We have introduced waves, and we said that this wave, our traveling waves, has an amplitude A, which is the maximum displacement, has a frequency uh, with the unit hertz, has an angular frequency radians per second that is also equals to 2 pi f. Period t is the time length for one full cycle, which is 1 over f. We have the wavelength, the length of this one cycle, and then we have the wave speed that is also equal to f lambda, the wave number radians per meter, k equals to pi over lambda, and we said that the traveling wave is going in the positive direction when the sign here is negative, or it goes in the negative direction of the x if the sign here is positive. Notice that this x defines the spatial variable where or axis where the wave is propagating along. So we've seen how is the traveling waves move in time steps, and we said that if we assume that this blue function is at t equals 1, then this dotted function would be at t2, which is basically the next time moment. In this case, what's going to happen to this point that belongs to the function right in here and on this space. So in this case, we said that when this wave moves, basically this point is going to move up, as you can see here. So the point is moving up in this case. Then we said that this traveling wave may see an obstacle that gets reflected from, and this reflection is going to cause some wave interference, and this is going to result into destruction and construction on that wave, which basically very similar to the principle of the superposition that you've seen earlier. In this case, you have two waves that will overlap. Sometimes they come in phase, and that's where they add. Sometimes they are opposite in phase, and there where they subtract. Okay, so in order to explain the interference, we can look at the superposition here of those two signals. One of them is incident, for example, and the other one is reflected. And here, if we use the principle of the superposition to determine the wave that results from the combination of those two waves when they meet or overlap, so when they overlap, they will result into a subtraction, and that's what we call destructive here. If this signal overlap with that signal is going to result into this signal. Why? Because they are out of phase, and in this case, this one would be subtracted from this one. It's going to result into a peak reduction, and that's why the peak will be somewhere like here, and this is what's happening here in D. So when we have two signal in phase, or what we call here overlapping, completely overlapping. In this case, we have a constructive interference. And in that case, those two signals, when I add them, if you look at those two signals, one of them is like this, and the other one is also right on it. Then when you add them, the amplitude will be double. So if this one is A, this one is going to be 2a, and as you can see here, this is what's going to happen also to the negative peak, and that's why we call it constructive interference. If it's destructive interference, or what we call sometimes, or what we call also out of phase, in this case, as you can see, if I am to overlap those two signals, then the signal is going to look like this. And in this case, if it's, as you can see here, out of phase, then the result is going to be zero. And this is what we call destructive interference. So the standing waves, what are those standing waves? Those standing waves basically are made of two waves. One of them is traveling in one direction, and then this signal has seen an a reflection due to obstacle at the end. It gets reflected back. When it's reflected back right at the reflection point, the amplitude here will be inverted, will be minus y. This is to satisfy what we call the boundary condition, because it has to be zero right at this point of the reflection point. Then in this case, the amplitude will be inverted. So this is where the minus came from. Then, as I said, if the signal is going into here, let's assume that this is a string that you tied it right at this point, and this is why the signal reflected is becoming zero, because the amplitude will have to be zero right at this point, and that's why the reflected signal will be minus a. So in this case, what's going to happen, if this is my positive direction, then here I have y equals to a sine omega t minus kx. Then the reflected signal, so this is for the traveling signal incident, then the reflected signal, so if I call this one incident, then the reflected signal will be minus a sine omega t. If it's going in the negative direction, then this will be plus kx. Now, those two signals, the incident that's coming in this direction, so this is the incident, this is positive. So let me put my coordinates here. X, Y. Then here is the incident, and here is the reflected. So the incident is positive, that's why we going in the positive direction, that's why this is minus. The reflected is going in the negative direction, this is why this one is plus. Now, if I add those two due to the interference, then the total signal would be a sine omega t minus kx minus a sine omega t plus kx. Now, if I look at a, take the a outside, then I have sine omega t minus kx minus sine omega t plus k. From the trigonometric identity, that is sine a minus sine b, we have 2 cosine a plus b divided by 2 times sine a minus b divided by 2. So if this one is A, and this one is B, then in this case, I have y equals to A 2 cosine omega t minus k x plus omega t plus k x divided by 2 times sine omega t minus k x minus omega t minus kx also divided by 2. Then I have y equals 2, kx is going to cancel, and I will end up with a 2 cosine omega t. Here, the omega t now here is going to cancel, so sine 2 minus 2kx divided by 2, or y equals to 2 minus 2a sine kx cosine omega t. So this is my standing wave. As you can see, it is made of a spatial variable here, kx, and omega t, the temporal variable. So in this case, this is my function, the one that I just derived, the function of time and space. And now this standing wave, as we will see, is the contribution of the spatial and the temporal. So this is the temporal and this is the spatial. So in this case, you will not see a traveling wave. What you're going to see is a wave that is vibrating in its place, and this is why we call it a standing wave shape. Watch this YouTube video. It shows you different experiments about the traveling wave and the standing wave in specific. So after you watch this video, you should be able now to understand that this is standing wave that is, as you'll see it, vibrating in its place, will have distinguished points such that those points, the displacement is always zero at those points, and that's why we call those ones nodes. They don't move, as if they're tightened to the x-axis, they have zero displacement. This is happening, why? Because of the constructive and destructive phenomena that we talked about, but those nodes are always zero because they represent the destructive points for the incident and reflected wave, and they're always zero. So this function now, if I am to go back to this function that describes the standing waves we talked about, and I took the sine kx that is responsible for the spatial function here. This is the one that is related to the locations along my x-axis. So those nodes are zero when kx is satisfying to the sign here. The sign is zero when kx is 0 plus when kx is 0 plus n pi. And in this case, n takes 1, 2, 3, 4, and so on. So in this case, this sign is 0 when x is 0. If I substitute now this n with the range here, then this sign would be 0 when x is 0, or x is uh, pi over k, or x is 2 pi over k, and so on. However, we know that k is 2 pi over lambda, then we will find, if you substitute k with 2 pi over lambda, the new values for those nodes would be x0, x lambda over 2, x lambda, x3 lambda over 2, x2 lambda. So every half a lambda, you have a node starting from this point, and then you go half a lambda, every half a lambda, you have a node. Now, the other distinguished points are those points right at the here. Those points, they reach a maximum of double the amplitude. Why? Because when they are constructive, they will add a plus a, and this now becomes 2a at the maximum, and then they go back to 0, and then again they flip. The positive becomes negative, and the negative becomes positive. However, they reach twice the amplitude. So those points, they always reach twice the amplitude. And those points, we call them antinodes. Those points are caused by the constructive interference. They always reach the maximum at one point in time. So the one that is responsible for this motion is the time function, the cosine omega t. The one that is responsible for the location is the sine kx. Now, if we go to this function again, and we ask when this sine kx is becoming maximum, when this sine kx is becoming plus 1 or minus 1, this is happening when kx is pi over 2 plus n pi, right? Where n here takes 1, 2, 3, 4. So in this case, if you substitute k with 2 pi over lambda again, you are going to get those 2 points. Again, it is not starting from 0, it's starting from lambda over 4 and then shifted half a wavelength. So it's a shifted half a wavelength. For the nodes, we started at the 0 and then went in lambda over 2 steps. Here for the antinodes, we start at lambda over 4, but we still go in lambda over 2 steps. The resonance is the frequency where you have the string, in this case, resonating to the maximum displacement. The lowest frequency for any string would be when this length equals to lambda over 2, and this is happening when n is 1, and that's what we call the fundamental resonance frequency. So the length of the string, when this length of the string equals to lambda over 2, this is the smallest resonance frequency you can get for a string. However, this frequency can increase, and those what we call the harmonics. However, the fundamental, so back to this expression that defines the length for the resonances, L equals to n lambda over 2. So when n is 1, this is the lowest frequency of resonance. In that case, the length of the string will equal to half lambda. That's why L equals to lambda over 2 is the lowest resonance frequency for any string. This frequency can increase, and in this case, it becomes the second harmonic, and this length will be divided into two equal lengths, or third harmonics will be divided into three equal pieces here. So the number of the harmonics is defined by the loop that you see here, or if you are looking only at one function, then you count the peaks. One, two, then you have a second harmonic. If you have one peak, then it is the fundamental frequency. If you have one, two, three peaks only for one function, if you're looking at one function, then you have a third harmonic, and in this case, n equals to 3. However, always remember that the lowest resonance frequency is when the length of the string equal to lambda over 2. Now, if we want to, work out this equation and write now the wavelength in terms of the length of the string, then lambda n will equal to 2L over n, where n is the number of the resonance frequency. If n equals 1, then this is the fundamental frequency, and then 2 the second harmonic, 3 the third harmonic. Now, if V equals to F lambda, then I can find now the resonance frequency for that string that has a defined length as n equals to V over 2L. F equals to n V over 2L, and L here defines the resonance frequency. If it's 1, then this will be the fundamental resonance frequency. 2 will be the second harmonic. 3 will be the third harmonic, and so on. So those harmonics are higher in frequency. So always remember, when the length of the string is lambda over 2, this is the lowest resonance frequency, and that's what we call the fundamental frequency. Now let's look at this example. Here things would be a bit clearer. We have a 50 centimeter long oscillating string. Establishes the standing wave shown below. The 5 waves shown are snapshots of the string taken at 0.012 seconds intervals. The displacements observed at 1 and 5 are the maximum displacement of the string. So what's happening here? At the first time interval, this is 1 is the function of the standing wave. And then the second time, as I said before, they kind of vibrate this way. So this one is decreasing, this peak is decreasing, this peak is decreasing. The third time interval, it becomes completely destructive. Why completely destructive? Because at that point, they are out of phase. At that point, they look like this. So if you do the superpositioning thing that we talked about, you are going to get 0. So this is number 3. And then what happens? They shift, and this shift is going to result into this peak now is switching, becoming positive. This one is going negative till it reaches the maximum negative, and here maximum positive. So in 5 time intervals, you can see this function flipping from minimum negative peak here to maximum peak positive at 5th time intervals. Now the question is asking, find the period, frequency, and wavelength for the traveling waves on this string. So in this case, this is 50 centimeters. We know that The period is the time it takes to the function to repeat itself. So repeating itself for that function means that it's going to start from 1, go all the way to 5, and then come back to 1. So in this case, it's going to take me, look, let's count how many time intervals. 1, 2, 3, 4, then coming back 5, 6, 7, 8. So in this case, I have the period t equals to the time interval, which is 0.012 seconds times 8, and now the period is 0.096 seconds. So this is the period. The frequency is the inverse of the period, and in this case, the frequency is 10.4 hertz. What else? We need the wavelength. The wavelength, we know that the length of one cycle is the wavelength, and here we have the wavelength lambda equals to 50 centimeter, because we can see that this full cycle is 50 centimeter, or what you can also say that this is resonating with a second harmonic. So if in this case the length of the string will be lambda, and in this case the lambda here would be 50, the length is 50, then this is second harmonics, then the length lambda is 50 centimeter. What else? B, what harmonic? In what harmonic is the string vibrating? It's vibrating in the second harmonic. How did we know that? We counted the peaks for one of them. So it has 1, 2, or in this case, if you have you can say it's this loop and this loop. We have two loops, so it is the second harmonics. What is the speed of the traveling waves on the string? So we all know that the speed is f times lambda. So we have the frequency 10.4 times lambda is 0.5, 0.5 meter, and in this case v is 5.2 meter per second. Now, the second example here, we have a traveling wave on a string with this equation, y equals to 6 sine 2 pi t plus 6x. It is reflected at an interface, and the reflected wave has the form of y equals to minus 6 sine 2 pi t minus 6x. What is the direction of the travel for the incoming wave? So we have the incoming wave here. This is my incoming wave, has a plus, which means it is in the negative x direction. So it is negative x. This is the incoming, this is the reflected. Since I saw a plus here, and this is x, then it is in the negative x direction. The second example, we have a traveling wave on a string, has an equation of the form, again, 6 sine 2 pi t plus 6x. It's reflected at an interface, and the reflected wave has the form y equal minus 6 sine 2 pi t minus 6x. The standing wave observed from the resulting interference is the third harmonic. What is the length of the string? The length of the string, we all know that in this case, when we have the L equals to N lambda over 2. Third harmonic means L equals to 3 over 2 lambda, right? And here, what is lambda? I have here k equals to 6. And I also know that k is 2 pi over lambda, which means that lambda is 2 pi over 6, or lambda is pi over 3. So if I substitute lambda here, then I have L equals to 3 over 2 times pi over 3, and the answer is pi over 2. So the answer is C, pi over 2. Example, we have a traveling wave. A traveling wave is oscillating at a frequency of 2 kilohertz and is shown at one moment in the time below. Which equation best describes this wave? We know that it is going in the negative x direction. So the sign should be positive. So let me write here. I have y. Amplitude is a sine omega t. And omega here is 2 pi ft. It is going in the negative direction, which means this is a plus k x. So let's find, so 2 pi f is 4,000 pi t plus. We only need to find k to get the full picture. So what we know here, that lambda over 2, if this is one full cycle, this is one full cycle, then this one is lambda over 2. And I know lambda over 2 equals to 4 from minus 3 to 1. So lambda over 2 equals to 4, which means lambda is 8 meters, right? So this k is 2 pi over lambda x. Don't forget, you need to make sure that you have the correct direction of propagation. So we have here x, then if you substitute lambda with 8, then this one is going to look like pi over 4. And the form that looks like what we have calculated is A. Last example for this lecture. The third harmonic of a string has a frequency of 120 hertz. What is the frequency of the second harmonic? The third harmonic has a frequency. So here F3 equals to 120 hertz. If I go back to my expression, that is Fn equals to N V over 2L. So if my F3 equals to 3V over 2L, and this is 120 hertz, then my second Fn2 equals to 2V over 2L, is F2 equals to V over L. Now, if I substitute V over L with F2 here, Then what do I get? I get 120 equals to 3 over 2 times f2, which means that f2 is 120 times 2 divided by 3 is 80 hertz. So the answer is SB.